intention is trying to get it done before class, but I never have time. I'm always doing other things. Geez, I need more hours in the day. All right, so yeah, a lot of this is going to be kind of FYI stuff, especially when we get to the graphing components where we talk about graphs, tangents, cotangents, secants, and cosecants. We will primarily be using the graphs of sines and cosine functions when we do our modeling. Can we, in fact, think of some things for future stuff to come down the road here? Can we think of a situation in everyday life, it happens every day, where sine or cosine curves might be used as a model to this particular situation? I'll give you a hint. It has to do with the big yellow ball in the sky. What about time? How would that model like a sine or a cosine curve? This whole big yellow ball moving through the sky thing.
If it's, well, depending on its height, you could tell the, what is it,
what? Well, it has to do with the time, right? Obviously, and even not so much on a daily basis, but looking over the whole year, right? What if we allow this axis, the vertical axis, to represent hours in a day? Hours of sunlight in a day. When do we have the most sunlight? Summer. In the summer, in June, and then the fewest hours of sunlight in December. If we were to actually track hours of sunlight over the course of an entire year, you would actually see a model of a sine curve. Yeah. What are some other models for sine and cosine functions? Well, in the engineering world, we could use a sine or a cosine curve to model this event. I'll give you another hint. Ready? It has to do with, this is a very vague hint. If you guys get this out in the press. P waves and S waves. Oh, man! Yeah, P waves and S waves. Primary and secondary waves for earthquakes, like when earthquakes rattle a building. You can actually model, for a short period of time, you can model that earthquake and the waves that go through the ground and strike a building with sine or cosine curves. Pretty amazing. But they actually don't last forever. They taper off. And this is another one. What if I had, like in physics, you guys probably do this in physics, the classic experiment of I've got a weight on a spring, and I pull the spring down with the weight, and I let it go. And what does it do? It oscillates, right? Does it do that forever? No, because it's dampening, it kind of eventually stops. But if it didn't, if it just kind of looked at a short period of time, or if it didn't dampen, it would oscillate forever, and that would model a sine or a cosine curve too. So eventually we're going to get to that stuff, the modeling component of what we're doing with these things. Today, though, we're going to look at the other function curves, and then introduce ourselves to these new four guys. Ladies and gentlemen, let me introduce you to the reciprocals. That's a great name for a band. So we have the tangent function and its reciprocal function of cotangent. And then these SEC. SEC is the secant function, and CSC is the cosecant function. And they are reciprocals of our sine and our cosine. Now, which is which? Well, obviously, these two, it's pretty easy to tell that they're reciprocals of one another, right? Cotangent and tangent. But how do we remember or know what the relationship is with the secant curve or a cosecant curve or a cosecant relationship? I don't have any bright ball in the sky. Here's the ultimate way to remember. I memorized the secant is related to the cosine, and the cosecant is related to the sine, because the letters are switched, the beginning letters. Cosecant, secant, or cosine and secant relates to something. I don't know. And then sine and cosine, or sine and cosecant. C. You might think S, oh, that's sine, and C for cosecant, that's cosine, but it's actually the reverse. So secant is the 1 over a cosine, and a cosecant is a 1 over a sine. So, I don't know, if that helps you think about it that way. If not, somebody comes up with another bright idea of how you remember which one's which. Let us know. You'll notice we're talking R's and X's and Y's again. Remember that these could also be O's and H's and A's for opposites, hypotenuse, and adjacent. But, so what happens in reciprocals, we know reciprocals mean to flip fraction over. And so if a cosine was a x over r, if I flip x over r and it becomes r over x, then we're talking about secant. And then sine is y over r, and if we reciprocal y over r, we get r over y, that's cosecant. And tangent. Now, we didn't do a whole lot on emphasizing tangent the last time we talked about the trig functions, but sine over cosine, or y over x, is our tangent function, opposite over adjacent. So if we flip those, we get x over y, and that's where the cotangent is going to come from. So if we have these memorized, these 6 trig functions, sine, cosine, tangent, cotangent, cosecant, secant, you guys are going to be great. You're going to be able to handle this stuff, not a problem. Now, the reason these 4 are unique is because, well, one of the reasons why they are unique is you'll notice that each of them have a condition where you can't be equal to 0. I can't be x equals 0 for tangent or secant. And if I was, it would be undefined. And then cotangents and cosecants, you can't have y equal to 0 because I'm dividing by a 0. So graphically speaking, when we have y's or x's, which are in the denominator, equal to 0, what do we create? When the 0 is equal to the denominator, you have a, what kind of asymptote? You have a vertical asymptote. So these 4 all have vertical asymptotes for their graphs. Where the sine and cosine, like the domain of the sine and cosine was all reals, right? Positive, negative theta. We didn't have any limitations on the x value or the domain values. These guys, we got to be careful. Can't be certain values. Oh. All right. When we move into chapter 8, which is going to be introducing you to trig identities, one of the things is going to be introducing you to trig identities. The next back there. Okay. We are going to have a relationship with sine and cosine for all of our trig functions, and here they are kind of given to you here. So tangent y over x, in the unit circle, y is equal to sine, x is equal to cosine. So we're going to start to relate these things, or we're going to begin to relate them in regards to sines and cosines. Eventually we'll get into other identities. Pythagorean identity is a big one, and then from there we develop other identity functions. So thinking of replacing y's with sines and x's with cosines, and r's we leave it alone because it's a unit circle, we make it 1. This would be the other relationship in terms of sine and cosine. So all right, like I said, a lot of information. What about our all support the covers acronym to remind us where the functions are positive? Since a sine and a cosecant are related to one another reciprocally, not even a word, then that means cosecant is the same place where sines are positive. And tangents and cotangents are related. So positive there, quadrant 3 for cotangent. And then cosines and secants related, positive for secant in quadrant 4. So they obey the same rules as their reciprocal relationships. That doesn't change here. Sorry, you guys in the back. All right, so nothing really dramatic right now, is there? Just one over stuff. 1 over cotangents, 1 over tangents, 1 over sines. Reciprocal, reciprocal, reciprocal. All right, so what if then we put ourselves in a situation where A and B, no calculator portion, or C and D, calculator portion, we're find out the values of these trig expressions here. What do we do? Let's try the A and the B without the use of our calculator. Hopefully you remember, based on the angle, remember that's where we start. Based on the angle, I know that I have, in this case, a 30, 60, 90 triangle. And then I hope that I remember that across from the 30-degree angle is the smallest side. The hypotenuse is always the largest side. And the other one's going to be a root 3. So for 30, 60, 90 triangle, we have that. Then I simply say, where am I? 30 degree, quadrant 1. My answer is going to be positive. Then I do this. I don't have a cosecant button on my calculator. So what do I do instead? I write this as 1 over the sine of 3. Because that's what a cosecant is. It's the reciprocal of a sine. So now I could put this in the calculator if it was a calculator portion, but you don't need to do that because you already know what the sine of 30 is. What's the sine of 30? Look at my triangle. 1/2. It is y over r, or opposite over hypotenuse. So it's 1/2. So if sine of 30 is 1/2, and I have 1 over 1/2, what must the cosecant of 30 be equal to? It must equal 2. So there are 2 approaches to doing these problems. This is one of the approaches. Rewrite it as a reciprocal, 1 over sine. The other way, it's essentially the same thing, but just recognize what the reciprocal function is. So we're talking about a sine of a 30, and the sine of a 30 is a 1/2, and the answer to that cosecant of a 30 would be the reciprocal of 1/2, which is 2. One of those 2 ways you're going to want to do it. And again, your calculator does not have cosecant, cotangent, or secant buttons on it, probably. Most of them do not. In fact, I'm not sure any of them have those. Now, they might have, or they will all have, cosine -1, sine -1, tan -1. Those are not the same thing as cosecant, secant, and cotangent. Those are what we call inverse functions. It does not mean reciprocal. We use those inverse functions to find the angles. And we haven't done any of that yet. So don't think that those cosine -1, sine -1, tan -1 buttons are the same thing as cosecant, secant, and cotangent. Okay, so somebody help me with this next triangle. What are my ratios for? Which triangle is this one, by the way? Tan of 135. Yeah, it is a 45er. And then what are the ratios here? All right. Yeah, we got to know this, right? Just like roll right up. So a tangent 135, that's not a reciprocal relationship. It's just a y over x relationship. And a y over x in this case means I have a 1 over 1, or 1. But tangent of 135 is in which quadrant? And in second quadrant, tangent is negative, so it should be a negative. There we go. Put yourself in the right place. Figure out your reference angle from your triangle if it is a non-calculator problem. And then, all sports covers, what am I supposed to be? Positive or negative. Now these next two would be calculator problems. Secant of 4, is this in degrees or radians? Yeah, remember there's no degree symbol, we're talking about radians. So secant of 4, cotangent of 6.5. So secant is the reciprocal of a cosine. So again, what's one way you could do this? One way you could do this is to go 1 over the cosine, making sure my calculator is in radian mode. 1 over the cosine of 4. Or just take the cosine of 4 and then write it as a reciprocal. Yes, ma'am. All right. Who's got that one? What's the answer there for secant of 4? Oh, first of all, where are we? Where is 4 radians? Third quadrant. Very good. Remember that 3.14 radians pi is on 180 degrees. So we're down here somewhere. There's my triangle that I created. So in that world where that's happening, I should be a negative value of this thing. So what is it? 1.53 roughly, since I ran out of space there. Negative 1.529, blah, 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 blah. So negative 1.53. You guys get that? No? Remember how you, again, one of two ways to get this. 1, divide, parenthesis, cosine 4, close parenthesis, equals. Or cosine 4, get that answer, and then hit my x to the negative 1 key or 1 over x pi. One of those two ways.
What mode do you have to be in again?
Radian, because we're in radians here. Did everyone get that? Yes? So how do I know that that's a quadrant 3? All right, so we have, here, we'll do it over here on this one. I ran out of room. So 0 pi over 2 is about 1.57. Pi, which is 3.14, 3 pi over 2, which is 5.71, and then 2 pi, which is 6.28. Okay, somebody still having trouble with the calculator? Are we all clear on the use of the calculator functions for? All right, so cotangent of 6.5. Where am I? 6.5 radians. What? You sure? Why am I in 1? Well, all the way around 1 time is 6.28 radians. I'm at 6.5. I'm a little past that. So I'm somewhere in here. All right, we've gone around 1 time, and then we've gone around a little more. Okay, so I should be positive here with my answer. So cotangent of 6.5, again, either take the tan of 6.5 and then write that answer as a reciprocal. Or do 1 divide by parenthesis, tan 6.5, parenthesis, and you'll get the same thing. So what is it? 4.5? 4.54? Did anyone else get 4.54? Okay. All right, so that's what we do with our reciprocal function. What questions are there on that stuff? Pretty good so far? All right. What about here? Put myself in a situation where I can draw the triangle in the right spot. Based on where that triangle is, figure out what are all of the trig functions. Sine, cosine, tangent, cotangent, secants, and cosecants. That's what we're doing here. So first, we've been given a couple things. One, we know what one of them is. It's already telling us the cosecant of theta is equal to this relationship, negative 17/15. Then, it also gives us this. And this tells us where we are. So I am going to be less than 90 degrees, but greater than negative 90 degrees. So what two quadrants am I in? 1 and 4. Less than 90, but greater than negative 90. So I'm going to be in 1 and 4 for this one. So we put ourselves in the right spot, first of all. We have our little sketch. It'll be 1 and 4. Now, this should be the giveaway. Which quadrant do I have to be in? Think about a cosecant. It's related to a what? Sine. So where sine's negative? Out of those two options. Fourth quadrant. So we're in the fourth quadrant. So we draw ourselves a little sketch of our triangle. There's our triangle. And let's put the parts of the triangle together based on what I have. So a cosecant of this angle theta. So here's the angle theta. We kind of did that. The cosecant, remember, is the reciprocal of a sine. So if a sine is a y over an r, this is an r over a y. And if my r over y is a 17 over 15, the r can never be negative. It's a radius. So that means this negative that's hanging out in front there is actually for the 15. So it's a 17 over negative 15. We can put those parts of the triangle in here. There's my radius. It's always the hypotenuse. The negative 15 is the y part of the triangle. And then now we have to go find the missing part, because I need to know what x is so that I can write all of the other trig functions that use x. Secants, cosines, tangents, and cotangents. All those guys need an x. So we got our triangle here. How do we find missing parts of a right triangle? Diagrams. So 17 squared, 289. 15 squared, 225. 289 minus 225 is 64. Square root of 64 is 8. So there's that missing part of the triangle, 8. Now I have all parts of the triangle. I have x. I have y. I have r. From those three things, I am now able to write all 6 trig functions. And maybe the only thing you need to do is just, as a reminder, think about your acronym. So my cosines and my secants and my tangents are going to be negative for this answer. But other things are going to be the cosines and the, did I say cosines? My sines and my tangents and my cosecants are going to be negatives. But cosines and cosecants, cosines and secants are positive. All right. Well, let's put them together. So let's start with cosine. Cosine of a theta is equal to an x over an r. And in our problem, our x is an 8 and an 8 over a r of 17. And then let's just below it, let's just put the reciprocal function. So secant is the reciprocal of cosine, and that's switch them, r over x, or 17 over 8. And then we do the same thing with the other, well, we only need 4 more of them. So we have cosecant already. So let's do sine. Sine of theta is y over r, which we know is negative 15 over 17. And that we could have picked up from the given information. Cosecant, just flip it. There's our sine. Then tangent is a y over an x, which in this case is a negative 15 over 8. And that means cotangent is an x over a y, which is a negative 8 over 15. So once we have our triangle and then the rest of it's just. What do you think? Difficult? Okay. So far, so good? You guys are all right? Okay, let's take a look at the graph. So here's where I'm just going to kind of go through this pretty quickly. If you want to come back and take a peek at the graphs in some detail, then I suggest going and check it out. Either the notes on Blackboard or the YouTube thing for this. Tangent graphs. Cotangent graphs. They are a little more on the unique side in the sense of they don't kind of derive themselves from our sine and our cosine graphs, or our cosecant and our secant functions do. They kind of come from those two. So we talked about the four functions that have vertical asymptotes. This is one of them. Tangent has vertical asymptotes where it has an undefined value, which means where x is equal to 0, and that happens at 90 and at 270 degrees. So every time I have a 90 and a 270 degree value, I'm going to have a vertical asymptote at that point. At the 0 and 180s is where tangent is equal to 0. Those are my x-intercepts. So if I simply plotted vertical asymptotes and x-intercepts, this is what I would get. X-intercept, x-intercept, so on and so on. And then you can see the vertical asymptotes through all of the negative 90, positive 90, 270, negative 270. Now, how do we know that the curve looks like this? You could put a generic t-table together, plug in your own values of theta, take the tan of that, whether it's in radians or degrees, and you're going to get enough points that generate these curves. Like some of the ones that are probably most useful or maybe known to us would be 45 degrees. Tangent of 45 is 1. So if I go over to 45 degrees, which is right there, and then I can put that into my calculator, I'm going to get a value of what? Or something like that. It's close to us. And then if I did negative 45 degrees, I'd have a negative 1. So I think these are in increments of 2. So I'd be right there. And then if I kept plugging in points, all right, let's say 60 degrees, and let's go 75 degrees, let's go 80 degrees, or let's go 15 and 30, and so on and so on. I'm going to get these points to create these curves. They kind of look like what function do those things look like? These green curves. They kind of look cubic. Yeah, they kind of look cubic. All right, but that means I would generate this. And so you can see that in the tangent world, unlike sine and cosine, which has a range value of negative 1 to 1, these have negative infinity to positive infinity for its range value. Everything works. Not so the case for a domain, but everything for the y. All right, I'm going to show you the other curves with the use of this little website here, just to see where they're coming from, and then we'll just give you the sketch. So here is where these curves come from if we think about our unit circle. So if we spin this, hey, you guys gonna have a conversation back there the whole period? If we spin this thing around, that circle, the point on that unit circle, which is measuring, or if we're measuring a y over x relationship, you're going to see these curves that are generated. The vertical lines you see there are obviously the asymptotes. All right, so there's how the tangent curve is created. What about a cotangent curve? How is it created using the unit circle? First of all, that's what a cotangent curve looks like. So y over x has become x over y. So now my vertical asymptotes have shifted. You notice they're not at 90 and 270 anymore. Now they're at 0 and 180 and 360. And my curve looks like the reverse or the opposite of the tangent. It's generated the same way, same kind of concept. Now you're measuring that x over y relationship instead of the y over x relationship. You get that. All right, what about these next two? I know I'm kind of rushing through this. You guys can kind of, if you want to check out this website on your own, kind of peek at it. So, sine and cosine curve, just a refresher. That's what they look like. Remember, cosine measures the x distance of that point as it spins around the curve. Sine measures the y distance as it spins around the curve. And so these are the sine and cosine curve. Cosine being this one. And if I took all of those points on that green cosine curve and then I just did reciprocals of them, I would be creating the secant curve, which looks like this. So again, where our cosines become 0, which are at 90 and 270, 1 over 0 would mean I have asymptotes at pi over 2 and 3 pi over 2 and negative pi over 2 and negative 3 pi over 2. And then if we did the same thing for sine, so anyway, there's the secant function. If I had a sine or cosine curve drawn in here, you can see how it relates to it. You can do that if you want on the graphic calculator. But anyway, there's your secant function. What about next? Cosecant, sine curve, took those sine curve values, took all the reciprocals of those points. Now my asymptotes are where sine equals 0 at 0, 180, 1 over those, make vertical asymptotes of those values. All right, so on and so on and so on. So those are the curves that result from sine and cosine. Taking the values, writing reciprocals of them, and getting those things. So cotangent or tangent, secant, cosecant graphs. Asymptotes pi over 2 plus every n pi for the secant graph. Asymptotes pi for the cosecant graph. And here again, if I were to draw in for the secant curve, which comes from tangent, where's 0 at? There it is. So it looks like this. This is the cosine curve typically. Right, that's a cosine curve starting at 1, going at 0 at 90 degrees, going down to -1 at 180. I took all those values, wrote the reciprocals. We did the same thing for cosecant. This time drawing a tangent curve in here, though, or a sine curve, starting at 0. There's the sine curve. And then reciprocating all of those values gives me those green guys. So this is more of an FYI. Again, the functions we're going to focus on, graphically speaking, are going to primarily be sine and cosine. But this is just showing you where these come from. What do I need you to know from this? How do we get the other trig functions? That's probably the biggest part of this section, is how do we get the other trig functions? So can you guys come up with these 6 for me? Let's see. We almost had a 6 out of 6 third period. Let's see if we can get a 6 out of 6 on the. What would the values be?